We are doing Lewis dot structures. These were the rules which we discussed last time. And today the aim is to learn hybridization, resonance, and VSEPR. So these are the three topics which are left of this unit 2. And once these are done, we can move to the next unit. So let's start with VSEPR, this one. For VSEPR children, I'm sending you some documents here. I want all of you, if you have your printer connected to your computer, so if you can take out the printout. So I'm sending some images here, PDFs. We are going to use it. One is this one. I'm sharing it here. Please download it. You can see this PDF here also. So formal chars, writing Lewis dot structure, that we have already done. So today we are going to do VSEPR. So I will explain you the meaning and then we'll start learning about whatever is written there. Okay. Hybridization, I'll start after that. So ready children? Take the printout. So before we start the VSEPR, let me tell you the meaning of VSEPR. Anil, you need it right now. If you can take the printout or open it somewhere in your computer. Because when you are answering the questions, you need it, right? So VSEPR, valence shell electron pair repulsion. V means valence. S means shell. E means electron. P means pair. R means repulsion. And then we say it is VSEPR theory. You know how to draw the Lewis dot structures now. We know all these rules. Like for example, if I say draw the Lewis dot structure of CO2. So you follow the rules. C is the central atom. Make the skeleton with 2 oxygens. Count the total valence electrons. Yes, total valence electrons. Carbon is 4, oxygen is 2 times 6, so 16. Complete the octet of this oxygen with minimum formal charge. So remember that oxygen can make 2 bonds, right? This oxygen can make 2 bonds. Now these are called as groups. So on this carbon, how many groups are there? Groups. On this carbon, how many groups? Count these groups. 2 groups. Now these groups are full of electron density. Can you see that I have made big electron cloud here? There are 2 groups on the carbon. We are talking about the carbon. So what are groups? Groups are atoms plus lone pairs on the central atom. On the central atom, right? Groups are atoms plus lone pairs only on the central atom. So this is the central atom, this one. On this central atom, you have two atoms. Any lone pair? No lone pair. So two groups, right? These two groups, they are full of electron density. So are they going to attract or repel? They are going to attract or repel? They are going to repel. Children, please answer questions, because I'm waiting for the answer and it's going to waste the time of the class. These are very simple questions. So I request all of you to answer it. If I get one answer, I'll continue my teaching, okay? So the electron groups, they have the same charges, so they repel. Now repulsion is not liked by the nature. So what nature would like to do? Nature would like to minimize the repulsion. So how can you put these two groups around the carbon so that they are far away from each other? The best arrangement is linear. These two groups are 180-degree to each other. That's the best possible arrangement of minimum repulsion. If you try to push them together, like you push them, you try to reduce this angle, then they repel more. So that's the minimum repulsion between two groups. And this particular arrangement is called as linear. That's what you are going to learn in VSEPR. Ready, children? Is the meaning clear to all of you? VSEPR, why these atoms, around the atoms, you have the groups. These groups are made up of electron pairs. These electron pairs, they repel each other. So according to nature, there should be minimum repulsion. So these groups would like to adjust themselves in such a manner that they have minimum repulsion. Which one you are talking about? This carbon? No. How many total valence electrons are there? 16. Carbon can make 4 bonds. It's already with 4. It's already with 4. It has used all 16. 8 here, 8 here. 8 plus 8, 16. So there is no lone pair on the central atom in this structure. Is it okay, Anil? If lone pair is not there, then you just say 2 plus 0. In this case, you will see many cases, Anil, where lone pairs are there. But right now, what you are going to say? 2 plus 0, 2, two groups. So this is, I have given you introduction. Now we can start properly. So I'm taking you on the whiteboard. So we are learning VSEPR. I have already given you the notes. VSEPR. Now you know the full meaning of VSEPR. Who is going to type it fast? VSEPR. Afan, Vivan, what's the meaning of this? Very good, Anil. Valence shell electron pair repulsion. Very good, very good. Afan, good. Theory. Theory means it's not a law. We are changing it. We have another theories. We have one more theory that is called as valence shell hybridization that you are going to learn. Then we have one more theory, molecular orbital theory, MOT, which you are going to learn in your college chemistry. Earlier it was there in AP also, but now they have stopped. So it will be in college chemistry, in organic chemistry, MOT, molecular orbital theory. So that's why it's a theory, it's not a law. And it's quite satisfactory explanation of the structures and the properties. Ready, children? So what are groups? Groups are lone pairs plus atoms. Where? On the central atom, right? On the central atom. These are groups. When you look at the groups, lone pair plus atoms on the central atom, it gives you electron pair arrangement. Electron pair arrangement, which you can see in my notes. We're learning a new topic, children, so please pay attention. Electron pair arrangement, which is called as EPA. Azuni, you're there? Okay, who else has not joined the class? EP, electron pair arrangements. See, children, this is the most important topic of AP chemistry. So in electron pair arrangement, you are going to count atoms and lone pairs, right? Okay, but after this electron pair arrangement, see, I'm placing an arrow here. If you look only after this, after deciding this, if you look only at atoms, then it is called as molecular geometry. And the aim is to know this molecular geometry. You know that they are going to repel each other, so they will arrange themselves to have minimum repulsion. So these molecules, they have a fixed geometries, shapes, molecular geometry, or you can call it as shape. But to know this shape or the molecular geometry, we should know electron pair arrangement, right? Like, for example, if there is a central atom and the central atom has only two groups around it, two groups. I'm talking about groups, children. So these groups can be lone pair and atoms, like this. Then the best arrangement is put groups. I'm writing groups here, children. When the groups are two, the best arrangement is linear with minimum repulsion. These are permitted by nature. If groups are three, then the best arrangement with three groups, we are deciding this. This is very important to decide. Only then you can proceed further. With three group children, the best arrangement is, can you see this? With the linear, the angle is 180 degree. But this one is called as trigonal planar or trigonal planar. Trigonal planar. This is with three. This I'm talking about with the groups. So what are these? These are EPA. EPA tells you the angle also. So what is the angle in this trigonal planar? 120 degree. Trigonal planar. All three groups are 120 degree to each other to have minimum repulsion, right? If the groups are four groups, then it is tetrahedral. You must have heard this name earlier. This is tetrahedral. Can you see? Draw it. You should be in the practice of making these shapes. This is tetrahedral. And the angle is 109.5 degree. 109.5 degree for tetrahedral for four groups. These are fixed. It doesn't matter who is the central atom and who is around it. You just draw the Lewis dot structure, count the groups. If groups are two, say EPA is linear, 3 trigonal planar, 4 tetrahedral. If groups are 5, I'm writing groups here again. Groups are 5. Then in that case, central atom A is surrounded by 5 groups. 3 will be in this trigonal planar like this. These are 3. 1, 2, 3. 2 are up and down like this. And this one is called as trigonal bipyramidal. Trigonal bipyramidal. Now children, you have to understand this name, that why it is called as trigonal bipyramidal. Pyramidals are non-planar, and these pyramids, they have a base. Like here, this particular pyramid, this one, it has a base. Can you tell me what is the name of the base? Look at the shape of the base. Isn't it trigonal? And what's the angle at the base? Angle at the base? 120 degree. Trigonal. This is the base. And then on this base, the group which is on the top here, this one, is making a pyramid. See, like this. Can you see the pyramid? Blue pyramid. This is one pyramid on the top of this base, right? Exactly in the same way, there is another pyramid with this one. So I'm making a three-dimensional picture on two-dimensional paper. So that's why it's slightly difficult to visualize. But can you see that in the center, there is a trigonal base. Then there is one pyramid on the top with this atom, one pyramid at the bottom with this atom. That's why it is called as bipyramidal. So all the pyramids are based on some base, and the name comes from there. Like you will see different names: trigonal bipyramidal, trigonal pyramidal, square pyramidal, square bipyramidal, like this. Pentagonal bipyramidal, pentagonal pyramidal. Pentagonal bipyramidal will not be the part of your learning, but easy to identify. If you're interested, I can give you example of that also. So is it okay? Group 5, trigonal bipyramidal. How many angles are there? Angles. The base is 120 degree. Can you see some other angle, children? It has more angles. You can see the angles. Okay. This angle is 120 degree. This is the base. The base. Flat, planar. On this base, this group is standing perpendicular. So this is making 90 degree with the base, with these atoms. And then it is also making one more angle with this one, these two. What is that angle, children? 180 degree. So can you see 120 degree, 90 degree, and 180 degree? Yes. Ashleisha, your answers are not coming. Okay, answer it, Ashleisha. Answer the questions. So we have understood the meaning of trigonal bipyramidal. Okay. Nivriti, you are there in the class? I think Nivriti is not here. So we are good with this. Now last group is group 6. In group 6, central atom A is surrounded by 6 groups. So 4 are in the plane. And what is this plane called as? Square planar. This is square planar, square base. Then one standing on the top, another standing at the bottom. So here also you can see two pyramids. The base is square. This is the base. Then it's making pyramids which are on the top here, like this. This is the pyramid. And it's making a pyramid here also. So it is called as square bipyramidal. What are you learning, children, right now? Electron pair arrangements, deciding from the number of groups. So we are going to do example of each one of them. So I want you to write down very clear about these EPAs which you are going to learn. This square bipyramidal has a different name and most of the teachers are using it. So they will not teach you this square bipyramidal, but I want to teach you because from here you can derive other names also. It's very important to understand the basic name, but more popularly it is called as octahedral. You must have heard about octahedral. Octahedral. Here the angle is 90 degree. Now I have given you the brief idea of EPA, electron pair arrangement. But from electron pair arrangement, finally I have to see the shape also. So ready for discussion, children? With different examples. Every time, please see how I'm drawing it. So focus on my pen and draw in your paper. It is very important topic going on, and most of the free response and MCQs are dominated by this part of the chemistry. Learning of the VSEPR, resonance, hybridization, and it's very simple. You need to just practice with me. Ashleisha, what is the angle here in a square? You know the diagonals. What is this angle? And the diagonals of a square are 90 degree to each other. Then this is perpendicular, so this is also 90 degree. Yeah, you can say one more angle, which generally books are not talking. Yes, we can say one more angle, 180. So 90 and 180, two angles. Square diagonals are 90 degree to each other. This is a square. These are the diagonals. So they are 90 degree. But if I compare this one, this angle between these two atoms, that is 180. If you see this is perpendicular, that is 90. Yeah, but main angle is 90 degrees. So we generally talk about 90. Yes, 180 is also there. So we are good with this. So ready? Okay, children, let's move. So now you should have your rules how to draw Lewis dot structure. So I will start with the group 2, which we have already decided as linear. Angle is 180 degree. So we are going to do these examples. Let's draw the Lewis dot structure of BeCl2. Central atom, Be. Skeleton, Cl, right? Total valence electrons, 16. Complete the octet of chlorine with 3 lone pairs. Very good. Check how many are used. Rule number 5, you remember how many are used? 8 here, 8 here. How many are used? All 16. You can check the formal charges. You see formal charge on everyone is 0 here. Formal charge, you remember the equation? So checking of the formal charge is important. Formal charge is the valence electrons minus number of bonds. I explained you in detail about the formal charge minus 2 times lone pairs. So beryllium formal charge is 2 minus 2, 0. Chlorine is 7 minus 1 minus 6, 0. Very good, Ashlisha. Very good, all of you. Perfect. Vivan, where are you? So we are good with this? Okay. So now how many groups around beryllium? Now pay attention to beryllium. Two groups. Two groups means they should be 180 to each other, right? Is there any lone pair on beryllium? No. So this is a symmetrical structure. Both the chlorines are identical. So I'm going to say that this is symmetrical. And not distorted by lone pairs on the central atom. So this is the language which I will be using a lot. Not distorted by lone pairs on the central atom, right? Check the bond polarities. Is this bond polar, this one? Is there a difference in the electronegativity of beryllium and chlorine? Who is more electronegative? Vivan, chlorine or beryllium? Look at the periodic table. You have done the electronegativity. So the bond is polar. So how to draw the dipole? Who is more electronegative? Chlorine. So it has a delta minus and beryllium has delta plus, right? So there is a polarity in the bond. That polarity, remember we discussed dipoles. Dipoles are vector quantities. They have direction and magnitude. I spent so much time on that 2.1 unit. Watch the video also. These are dipoles. So there is a dipole here in this direction, correct? With some magnitude and direction is fixed. Exactly same dipole is there in the other direction because this is also chlorine and is exactly opposite direction, right? These two dipoles are pointing in opposite direction with equal magnitudes because atoms are identical. There is no distortion on the beryllium due to lone pairs. There is no lone pair. So the net dipole moment, if you remember the word net dipole moment, this is mu, net dipole moment, which is the sum of all dipoles. Net dipole moment here is 0. So the molecule is polar or non-polar? If the sum of all dipoles is 0, molecule is non-polar. We have started a topic which we are going to learn in unit 3. Non-polar means the whole molecule has no polarity because all dipoles are cancelling out. And dipoles are due to, yes children, these dipoles are due to polarity in the bond. And polarity in the bond is due to difference in electronegativity. Yes, difference in electronegativity, right. So whenever we say the molecule is symmetrical, then you must see that it should have identical atoms around it. Symmetrical, identical atoms. Not distorted by lone pair. So then you will say, oh, okay, there is no lone pair, so there is no repulsion. Lone pairs are going to repel more because they are not shared by two atoms. So their electron density is very high. So they can create more repulsion to rest of the things. So they distort the shape. So no distortion. So then these kind of molecules will be non-polar. Children, is it okay? Because they are going to have net dipole moment equal to 0. So I will be using this. You will draw the structure. You will say, oh, it is symmetrical. Oh, it has no lone pairs on the central atom. So it means there is no distortion. Few exceptions are there, which you will learn. So it means it's non-polar. We are good with this? Anyone has any problem? Ready for another example? We are working with group 2 children. I'm giving you different examples. We are writing the Lewis dot structure. We are checking the polarity of the bonds. We are checking EPA, electron pair arrangement. And here there is no lone pair. So what is the molecular geometry, children? What is the molecular geometry of this molecule? There is no lone pair. The molecular geometry is also linear. Yes. Symmetrical, not distorted. Net dipole moment 0. Non-polar molecule. We are good? Ready for next? So here comes the next one. CO2. Remember I started with this example. Central atom. So first you draw the Lewis dot structure. Using the rule, central atom is carbon, skeleton with 2 oxygens, total valence electrons, carbon is 4, oxygen is 6, so 2 times 6, 16. Complete the octet of oxygen with minimum formal charge. Oxygen can make a double bond with 2 lone pairs. You remember that? Azuni, here also a double bond. How many are used? 8. 8. Is anything left out of total valence electrons? No. Is there any lone pair on the central atom? No. Rule number 5. Central atom is carbon. It can make maximum 4 bonds and is happy. Check the formal charge on every atom. Formal charge on oxygen 6 minus 2 times 2. Same here. Formal charge on carbon 4 minus 0. So everybody is with 0 formal charge. That's the best structure for CO2. So what is the EPA, electron pair arrangement? How many groups on the central atom? Groups. 2. What is EPA? Electron pair arrangement? Linear. Very good. What is molecular geometry? Because there is no lone pair, right? Same linear. Same, right? Any distortion by lone pair on the central carbon? So is this molecule symmetrical? Molecule is symmetrical, not distorted. So it's a symmetrical linear. So what's the net dipole moment for this molecule? 0. So the molecule is polar or non-polar? Non-polar. Understand this, children, right? So we are going to discuss this now. Why this is non-polar, this part. So carbon, oxygen, which one is more electronegative, carbon or oxygen? So there is delta minus here, right? Delta plus here. So draw the dipole like this. Draw the dipole on the other one also like this. So can you see that they are in different directions? Yes, Ashlisha, they are in different directions. So what is the net magnitude? Mu equals to 0, right? So the net dipole moment of this molecule is 0. So molecule is non-polar because all the dipoles are equal in magnitude and pointing exactly opposite to each other. The vector sum will be 0. Okay. Now let's do another example. COS. COS. Central atom. Yes, children. Central atom. Carbon. Skeleton. Total valence electrons. 4 plus 6 plus 6. Check the periodic table. 16. Anyone has any problem in the valence electrons? Complete the octet of oxygen, most electronegative. You know that is very happy with a double bond, right? Complete the octet of sulfur now. Sulfur is brother of oxygen. In the same family, it is also very happy with the double bond. But when you are making the double bond, take care the central atom should not have any objection. No, it has no objection because it can make 4 bonds maximum, 4 valence electrons, 4 bonds, right? Check the formal charge on every element. Formal charge, children. What's the formal charge on this? 0. What's the formal charge on this? 0. Arjun, don't try to answer so fast. Please stay with me, okay? It disturbs the class. Arjun, stay with me because your answer is wrong. So how many groups around carbon? How many groups around carbon? 2. Arjun, 2. This carbon. Groups. Groups are atoms and lone pairs. So 2 groups. So when the groups are 2, then it's linear. What is linear? EPA. But is there any lone pair on the carbon, central carbon? No. So what's the molecular geometry? Linear. But the next question, is this molecule symmetrical? Is this symmetrical? No, it is not symmetrical. Because you can see one side is oxygen, other is sulfur. So there is a dipole here which is bigger because oxygen is more electronegative. And there is a dipole here which is smaller. So they are not equal in magnitude. So if they are not equal in magnitude, do you think the net dipole moment is 0 or not 0? It's not 0 because they cannot cancel out each other completely. So the molecule is polar or non-polar? It is a polar molecule. Children, you are understanding this? It is big thing in unit 3. So that's why I'm giving you practice starting from here only. Okay, good. Ready for next? Now this is linear, 2 groups. In the linear 2 groups, if you see the PDF which I have given, there is no lone pair example. Like there are like this, I can have a one example like this, A bonded to B and it has a lone pair. So if I ask you that how many groups? 1, 2. But actually there is no shape here. There's a line only, right? So generally we don't talk about it. Yes, Arjun. Anil. So we generally don't talk about these type of examples. So there is only one example that is linear. It can be symmetrical, it can be not symmetrical if atoms are not identical. So ready for next? I'm taking you on the next example. That is 3. 3 groups. Do you remember for the 3 groups what I said? 3 groups, children. What is the EPA for the 3 groups? Trigonal, planar, like this. Angle is 120 degree. Here I'm going to show you 2 scenarios, 2 different scenarios. First, let's make the Lewis dot structure of BF3. BF3, central atom, boron, skeleton. Remember, fluorine can never be the central atom. Fluorine can never make a double bond. We discussed this, right? Okay, now count the total valence electrons. Boron is 3. Fluorine is 3 times 7. You can see boron has used all his 3. 21 plus 3 is 24. Complete the octet of fluorine. It can make only single bond. So it's going to have 3 lone pairs, right? All of you are listening? Please draw it in your notebook. How many are used out of 24? All 24 are used. What is left? 0. Means we are done, right? Now count the groups around boron. How many groups around boron? 3. Any lone pair? This is not distorted by lone pair. It's a perfect symmetrical shape. It's symmetrical, children. All atoms are identical, you can see. It's symmetrical. The bonds are polar. Chemical bonds are polar, yes or no? See the difference here? They are polar. So draw the dipoles. This is a symmetrical shape given by nature. Trigonal planar. If atoms are same and there is no lone pair, it's symmetrical. All bond dipoles, these are bond dipoles, bond dipoles. So the bonds are polar, but the molecule is non-polar. You're getting it, children? This is a question. Pick up an example where bonds are polar, but molecule is non-polar. Molecule is non-polar. Is it clear to all of you? This is one example. So what is the EPA here? EPA is trigonal planar, TP. We can write TP, okay? Short form. What's the molecular geometry? Is also TP. There is no distortion by lone pair. Now, I'm using this word distortion by lone pair, but I have not given you any example. Now let's go for an example. This is one scenario with 3 groups that all 3 are atoms. All 3 are atoms. One scenario. 3 atoms. There's another scenario. 2 atoms and 1 lone pair. Then things are different. These things will remain the same. There will be no change in this. But molecular geometry will be changing when you have 2 atoms, 1 lone pair. Ready for example? SO2. Central atom, sulfur. Skeleton, 2 oxygens, right? Afan, come back fast. So I don't know what is the shape. I don't know anything. So I'm just making like this, 2 oxygens. Total valence electrons, 6 plus 2 times 6, 22. Oh, 18? 18. Yes, not 22. Sorry. Who is saying 22? Arjun, Naisha? Okay. Now complete the octet of oxygen with minimum formal charge. You know, it's very happy to make double bonds. Sulfur has no objection because sulfur has 6 valence electrons. It can have expanded octet. It can make maximum 6 bonds. So right now it's making only 4. That's fine with sulfur, right? Put 2 lone pairs on each oxygen. Vivan, Afan, we are good with this? Afan, you're back? And then on sulfur, how many are used? 8, 8, 16 are used. How many are left? 2. They will go as a lone pair on sulfur. Count the groups on sulfur. Groups means, yes children, groups means lone pair plus atoms. On sulfur, don't include that of oxygen. Groups on central atom. Okay, some children, they start counting these also. No, on the central atom. So they are 3, right? So what is EPA? EPA is trigonal planar. So it means this is not like this. The molecule is not like this. How is it? Like this. Put it like this. 2 oxygens, right? Like this. This is EPA. But what is here? A lone pair. A lone pair, like this. right? So EPA is trigonal planar. So, but actually, this is not a bond. These lone pairs are in the orbitals of the sulfur. You see, I made the orbital here. So, this bond I will replace and I'll put a lone pair here. I didn't get what I was saying. Aishleisha, what are groups? Lone pairs and atoms. Okay, so can you see that? Aishleisha is asking a question, children. Sulfur, how many atoms on sulfur? Aishleisha, answer my question. How many atoms? Okay, she's not answering. Children, can you answer? How many atoms? No. How can you say that sulfur has two lone pairs? Atoms are these. These are atoms. Atoms, oxygen atoms. There are two atoms and one lone pair. So total groups, three. Three means trigonal planar, right? Trigonal planar means you're going to draw it like this. Sulfur with three groups like this, trigonal planar. Out of these, two are doubly bonded oxygens, right? Yeah, I'm telling you from the starting, from here only. Groups, lone pairs plus atoms on the central atom, right? Children, if you have these kind of doubts, please stop me and ask, because if you are struggling here with the lone pairs and atoms, then you won't be able to understand anything. So those who are having any doubt anywhere, you can stop. It's going to help you. But now lone pairs are not going to make a bond. These lone pairs are here. They are not making a bond because there is no other atom. So they are actually residing in the orbitals of sulfur like this. This is the orbital of sulfur. It's not going to provide any shape. So it will appear like this. This is the shape. So what is the shape? The shape is bent. Is it a symmetrical shape? No. Two sides oxygen, one side lone pair. It is unsymmetrical. So whenever your molecular, this is molecular geometry. So what is the molecular geometry of this molecule? Bent. It's not trigonal planar. So it's not symmetrical, not symmetrical, because one side is occupied by lone pairs. And these lone pairs are distorting the shape. It's distorted by lone pair. Yes, not symmetrical. So unsymmetrical, we can say, because all the three groups are not identical, right? So there is a dipole here due to lone pairs. They also exert a dipole, big dipole here. And there are two dipoles here due to oxygens. So all the dipoles are not exactly same. So the net dipole moment is not equal to zero, right? So this molecule is polar or non-polar, children? This molecule is polar or non-polar? It is polar. Because the net dipole moment is not equal to zero because it has a lone pair which has distorted the shape, and all the three atoms are not identical. So bond dipoles, see the language, bond dipoles do not cancel. So the net dipole moment is not zero. So we are okay with the two examples of group 3. Two examples of group 3. Ready for one more? One question here. See, I'm giving you plenty of examples. All these examples are really good. SO3. Can you draw the Lewis dot structure of SO3? Central atom, S, skeleton, 3 oxygens, Total valence electrons, 6,4 of sulfur, 3 times 6,4 oxygen. So it is 24. Yes, Lisha, 24. Complete the octet of oxygen so you can make double bonds. How is it feasible that I can make so many double bonds around sulfur? Give the reason. I'm making, how many bonds I'm making around sulfur, children? How many bonds I'm making around sulfur? 6. And you know that sulfur has 6 valence electrons. It can have expanded octet. It can make 6 bonds. So no problem, right? Sulfur has no problem. Check the formal charge on sulfur. Check the formal charge. 6 minus 6 minus 0 is 0. See? Sulfur has no problem with this expanded octet. Oxygen, formal charge, 6 minus 2 times 2, 0. Everybody is with 0 formal charge here, right? Who is going to tell me that why sulfur can have expanded octet? Any one of you? Sulfur, phosphorus, second period elements. No, not second, third. Third period elements can have expanded octet. Why? Because they have. Yes, why, Anil? Question is why. Why? Question is why. I told you that you memorize it properly. But why it can have 6 excited electrons? Why not oxygen? Because of the, no one is giving me the right reason except Aslisha is very close to the right reason. Because they have empty d orbitals. And rest of you, Azuni. Yes, you can have 6 unpaired electrons because of the presence of empty d orbitals. If empty d orbitals are not there, then you cannot have so many electrons unpaired. So understand this. Azuni, so many children are not participating. Afan, Ariba, Naisha, Vivan. Okay. You didn't answer, any one of you? Vivan answered, yeah. Afan. Afan, are you there? You have come back? Yeah, but you didn't answer anything. You answered that it is empty d orbitals. Did you answer that it's empty d orbital? No, I didn't see. So answer every question. Try to answer every question. Class is for everyone. Okay, now children, count the groups. Answer here, Afan. How many groups around sulfur? 3. So when the groups are 3, what is the EPA? Groups 3. EPA? Trigonal planar. From EPA, decide the angle. Angle 120 degree. What's the molecular geometry? Any lone pair? So molecular geometry is also trigonal planar. Molecule is symmetrical. This one? Symmetrical. All atoms are identical. If it is symmetric, the net dipole moment is 0. So remember this line also. So the molecule is nonpolar. I think now you people are catching it. So we are done with groups 3. So in group 3, there are 2 shapes. If all 3 atoms are, all the 3 groups are atoms, then it is trigonal planar. All atoms are, all groups are atoms. But out of 3, if one is lone pair and 2 atoms, then it's going to be bent. This example, bent. Is it okay? Okay, now let's come to the 4. Groups are 4. So can you recall when groups are 4, then what is the EPA? Electron pair arrangement. Tetrahedral. Tetrahedral. Tetrahedral is like this, right? All groups are 4. Now here you see what are the different combinations and try to understand that. All 4 groups are 4 atoms. There is no lone pair. Out of 4, 3 atoms and 1 lone pair. That is another situation. This is also 4. And out of 4, 2 atoms and 1 lone pair. 2 lone pairs, sorry, not 1, 2. You can see this is also 4, this is also 4, this is also 4. Agreed, children? Just look at these numbers. 3 atoms, 1 lone pair, 2 atoms, 2 lone pairs, right? Now let's see that if all 4 are atoms, then there is no distortion. It's going to be a perfect tetrahedral like this. So what is the molecular geometry? When all 4 are atoms, tetrahedral. If atoms are identical, then it's a perfect symmetrical tetrahedral. If it is symmetrical, then dipole moment will be 0. If it is symmetrical, right? Right now I cannot say because maybe the atoms are different. You're getting it? But if out of 4, so out of 4, 1 is lone pair. So what do you do? This is a central atom. 1 is lone pair. Put the lone pair like this. Is it tetrahedral? No. Remember I was telling you to understand the pyramids. No, it is not bent, Anil. Bent is planar. Check here. It's not planar. What is the base here, children? Name the base. Isn't it a pyramid on a base? Name this base. Trigonal. And the top is the pyramid. So what's the name of this particular shape when you have 3 atoms and 1 lone pair? Trigonal pyramidal. Yes. Trigonal pyramidal. That is the reason I want you to understand the meaning of pyramids, how they are named. Right? Now, that's the situation when you have, so please understand this because I'm going to ask questions. Is this symmetrical? Do you think you can have some symmetry here? No, because one side is occupied by lone pairs, which is going to cause a big dipole, and they are not cancelled by other groups. So it means this is always going to be unsymmetrical, and the dipole moment is always going to be not equal to 0 and is going to be polar always. I didn't write here because here it depends what are the atoms, right? But here always non-polar. Is it okay, children? Let's do the next one. Come back on this tetrahedral, this one. Replace 2 bonds by lone pairs. So what is left? Like this. You can see 4 groups. 1, 2, 3, 4. Right? So what is it? What is appearing to you, children? Is bent. But you said that bent was here also. Remember this bent? Bent. What's the difference in this bent and the bent I was discussing? This bent has only 1 lone pair. Yes, this bent has 1 lone pair. The other bent has 2 lone pairs, right? And having 2 lone pairs means other bent is tetrahedral. It is EPA was tetrahedral. This bent has an EPA of trigonal planar. So what is the angle expected in trigonal planar? 120 degree. So what is the angle expected here? 120 degree. But due to lone pairs can cause distortion. Due to these lone pairs, these bond pairs are pushed together and angle will be slightly less than 120 degree. Slightly less. Then it will stay closer to 120 degree. But it will not be exactly 120 degree because lone pairs, they need more space. So they will try to occupy more space and they will push them closer. You're getting it, children? So here in this band, angle is closer to 120 degree because it was out of EPA of trigonal planar. But over here, this band is the outcome of tetrahedral. In tetrahedral, the angle is 109.5 degree. You remember I told you? So is the angle exactly 109.5 degree? No, it will be less than 109.5 degree. Who is going to give the reason? Why? What's the reason? Why? Because it is distorted by lone pairs. The shape is distorted by lone pair. What are you expecting here? Angle. Children, angle. In this case, trigonal pyramidal. Less than 109.5 degree because it is also distorted by lone pair, right? In which case distortion is more. In the bend. And what are you expecting here? The angle when there is no distortion by lone pair. What is the angle here? Exactly 109.5 degree. Afan, is it okay? Afan, your answers are not coming. Yeah, but keep answering the questions also. So now I have done the explanation part. Everything is written in front of you. You didn't ask any question when I was discussing this. So I take it that everybody has understood. Now your turn, children. Answer my questions. There are three molecules I'm going to give you based on these three molecular geometries. Three molecular geometries. So in the tetrahedral EPA, there are three molecular geometries. What are those three molecular geometries? One is tetrahedral. For tetrahedral, you can write TD. Other one is trigonal pyramidal, like this, TPY. And third is band. This has all four atoms. This one has one lone pair, three atoms. And this one has two lone pairs and two atoms. Is it okay? Lone pairs, they are more aggressive because they are shared by one atom only. So nuclear charge is less. So they need more space. So they push the bond pairs together. So bond angles, they tend to go less, means bonds are coming closer. So angle reduces. Ready? CH4. Draw the Lewis dot structure. Center atom. Skeleton. Total valence electrons. 4 plus 4 times 1, 8. How many are used? All 8. See, all 8 are used here. Check. And you remember that hydrogen cannot have lone pairs. Hydrogen cannot make more than one bond because it has only one valence electron, one S1. There is no lone pair also. Okay, so this molecule is done. So how many groups around carbon? 4. So it goes in first category. What is the EPA for the molecule? Tetrahedral. What is the molecular geometry for the molecule? Tetrahedral. Is the molecule symmetrical? Not symmetrical. The molecule is symmetrical. There is no distortion by the lone pairs. Symmetrical. All atoms are same. Symmetrical, right? Polar, non-polar. If it is symmetrical, net dipole moment. Children, you know this? What is this called as? Please type it here. I have written it so many times. Let me see how many of you know this. Net dipole moment. Very good, Aslisha. Net dipole moment is 0. So the molecule is polar or non-polar? Non-polar. No polarity in the complete molecule. Like this. Ready for next? Your favorite water. Central atom here. Here, central atom is? Yeah, because hydrogen can never be the central atom, right? So oxygen. Skeleton, right? Count the total valence electrons. 8. Complete the octet of oxygen first. Hydrogen is already done. 2 lone pairs. Count the groups around central atom. Afan, groups around central atom. Okay, I think he was answering lone pairs. Yes, 4. 4 groups. 4 means, what is the EPA? EPA. EPA for 4. Tetrahedral. But you can see that if I make a tetrahedral on this oxygen, see how I'm making it. Some children, they say that why you're making it like this. This is tetrahedral. This is how you make a tetrahedral. So here is a lone pair. Here is a lone pair. These are hydrogens, hydrogen. These lone pairs, they are in the orbitals of oxygen, like this. They need more space, so they push them more closer. So there is distortion, right? So I'm going to put the lone pairs on the oxygen. So this is how you see water in books. So what's the shape? EPA is tetrahedral, molecular geometry is bent. Is angle closer to, is angle 109.5 degree or less than that? Angle is less. You know water has an angle of 104.5 degree. Children, they know it very well. But it's closer to 109, not to 120. Because the EPA is tetrahedral, that's why angle is closer to 109. Right? Azuni? Yeah, good. Very good, Azuni. Perfect. So children, don't mind if I'm calling your name and you have just answered, okay? Because generally mothers are always doubtful of their children. So same is here. That what are you doing? Okay, so this is water, right? We are good with this? And is bent. Is it symmetrical, not symmetrical? Answer it. Symmetrical, not symmetrical? Not symmetrical. If it is not symmetrical, then the net dipole moment is? Net dipole moment is equal to? Is not equal to 0. So molecule is polar, non-polar. Water is very polar molecule. It has a very high dielectric constant. That's why it is a good solvent. It can dissolve everything in it. Universal solvent because of its polarity. And you will learn this solution solubility in unit 3, which is based on learning on this, what you are doing right now. Okay, another example, children. So I'm making another example here. And that is NH3, ammonia. You know ammonia, right? Central atom here, children. Skeleton. Count total valence electrons. Total valence electrons. 8. How many you have used? And complete the octet of the nitrogen because that's more electronegative. Out of 8, how many you have used? A bond means 2 electrons, not 1. This is a bond pair, right? Pair. You remember I was using the word pair, bond pair. So how many I have used? 6. You can see nitrogen octet is not done. So there is a lone pair on nitrogen. Check the formal charts. Now all 8 are used. All 8 are used, right? A fun, you're going to count them as pairs. Pair means 2 electrons. So check the formal charge on nitrogen. 5 valence electrons, 3 atoms, bonds, these are bonds, and 2 times 1 lone pair. It's very happy, right? Formal charge is 0, happy situation. Okay, count the groups around nitrogen. Groups. So what is the EPA? Who is saying 3? Afan. Afan 4, you are going to count the lone pair and atom. So the central atom is nitrogen with 4 groups. So what is the EPA? Tetrahedral. So I'm going to place hydrogen here and a lone pair here. But this lone pair is not a bond, right? So what I'm going to do, I'll replace this bond and put the lone pairs in the orbitals of nitrogen. Now from here, decide the molecular geometry. Molecular geometry, children. Trigonal pyramidal. Is it symmetrical? Trigonal pyramidal. Is it symmetrical, children? Not symmetrical, never. Trigonal pyramidal, any molecule with trigonal pyramidal is distorted by a lone pair and is not symmetrical and is always going to be polar, right? You will learn so many geometries, so many examples of exactly same geometry. So whenever you see anything with trigonal pyramidal, straight away you can say, oh, it's not symmetrical, distorted by lone pair, and it's definitely going to be polar in nature. So it is not symmetrical, right? Not symmetrical means net dipole moment is not equal to 0, means polar, right? Okay, we are good with this. These are the examples of your groups 4. 4 groups have 3 molecular geometries. 1 tetrahedral, second trigonal pyramidal, third band, based on how many atoms and lone pairs are there, right? You can memorize them. I've already given you that sheet. You can check them. Like in linear, there was only 1 molecular geometry, but in trigonal planar, there were 2. One was perfect trigonal planar, the second was bent. Then it's a line, Aslesha. That's what I said. That's why linear, I said in linear, I have only 1 geometry. Because if you put 1 more lone pair, then it is a line, isn't it? Then there is no shape. Line doesn't have a shape. Then we don't discuss molecular geometry. So generally, we need minimum 2 bonds around the central atom. Only then you discuss angle. This has an angle. But if I make a line like this with 3 lone pairs, where's the angle? Where's the shape? No shape, no angle, right? Ready for one more example? So who is going to create more problem in the shape? The bond pairs and the lone pairs. What is the reason? What is the reason? If you look at the lone pairs, they are attracted by 1 atom, that oxygen. They are not attracted by 2 atoms, so they have less attraction. So they cause more repulsion. They cause, Anil, you should know this reason, okay? Lone pairs are attracted by 1 atom. So they have less attraction on them. Less attraction means they can cause more repulsion. More repulsion means they would like to occupy more space. They spread out more. When they spread out more, they push the bond pairs closer. Everybody, please pay attention to this, what I'm teaching. Understand the nature of lone pairs. Somebody who has less attraction means more energy, more repulsion, needs more space. They want to take more space to minimize the repulsion. But Azuni, this is very important topic going on. So please Watch the recording. Okay, the last part. It's very, very important. You're doing good. Children, you have stopped doing quizzes. You can go, Aswini. No problem. Children, please start doing the quizzes. All of you have done unit 1. How many you have not done the unit 1 completely? How many of you have done unit 1? Because now I'm back to my home and I'm going to declare the result of unit 1. So still you have one more day. You can finish it. Otherwise, I'll take out the result and show it to the parents. Okay. So I was talking about the lone pair. So lone pair, they cause more repulsion. That's why the shape becomes distorted. Angles, they become lesser. So can you tell me in ammonia and in water? Water, I have already given you angle, 104.5 degree. 104.5 degree. And this ammonia. What can be the angle in ammonia? Is it going to be more than 104.5 degree? Or is it going to be exactly 109.5 degree? What are you expecting? You see, there is only one lone pair for distortion. So angle will be less than this, but more than this, right? And it's a very popular angle again, children. This angle in ammonia is 107 point something. So I'm just citing approximate. 107. Can you see 107 is less than this, more than this? So they may ask you this question. They will give you these angles and they will ask you that how come ammonia has slightly more angle than water and why they don't have exactly same angle. Then you have to explain the nature of lone pair, right? Then you will see that in this case, lone pairs are more. So they need more space. So they cause more distortion and they push bond pairs more closer. Angle goes down. Here there is only one lone pair. So that's going to cause less repulsion as in water. So angle will reduce, but it will be slightly more than that of water. Afan, you heard what I said? Okay, sorry. Now, coming on the next one, because we are left with less time. So I'll give you a brief introduction today and we'll continue from here in the next class. You remember 5 groups? 5 groups. So in 5 groups, what was the EPA? Trigonal, pyramidal. That was the EPA. Okay. And not pyramidal, sorry. Sorry, I just saw what Anil is writing. Trigonal bipyramidal. Sorry, bipyramidal. If you remember, this is the central atom. So 3 on a trigonal base and 1 above, 1 below. Then I explained you that why it is called as trigonal bipyramidal, because it's making a pyramid, this one, with the base, trigonal base. See, this is the trigonal base, this one. This is the trigonal base. You can see this pyramid on the top. Similarly, this one, right? So that's why it is called as trigonal bipyramidal. We are good with this? Okay. Now here there is a problem. Angles are different. Do you remember the angles? What are the angles? 120 degree and 90 degree. These are important. And then only these two atoms are 180 degree. So these are the angles, right? Okay, so 120 degree is more. There are 90 degrees more, in fact, 90 degree. How many 90 degrees angles are there? See, with this atom and this A and this atom, what is this angle? 90, right? This one. Similarly, with this atom and this one, what is the angle? 90. Same with this, 90, 90. So Aslesha is saying 6. 1 with this, 2, 3. She's right. 6, 6, Anil. See, okay, those who are not understanding, pay attention. Vivan, you're there? This one with this one. One angle. Now with this one. Second angle. Now with this one. All these are 90 degree. Is it okay? All these are 90 degree, right? Now this one is making 90 with 3 atoms. Similarly, this top one is also making 90 with 3 atoms. So total 6. Total 6. You can rejoin the class, Naisha. So we are good with this? Okay. Now, you remember the story of the lone pairs? Lone pairs are more aggressive, more unstable. They need more space. They need more space. They try to distort the shape. More space means with more space, repulsion is less because they try to spread out to minimize the repulsion. So lone pairs want to stay away from each other because they can cause repulsion. So they need more space. They should be on more bigger angles. More bigger angles. Here, if you see, just leave this 180 degree. Here you can see, children, now please pay attention again. I'm teaching you a very good thing here. In this structure, trigonal bipyramidal, these are two types of bonds making 90 degree with the base. We call them as axial. So how many axial bonds are there? 2. And they are making 90 degree angle with the base, right? Then there are 3 on the base, which are 120 degree with each other. And we call them equatorials, which are on the corners of a triangle, equatorials. So how many equatorials are there? 3. Axials, 2. So whenever we have lone pairs, where would you like to place the lone pairs? That's the question. Lone pairs are problem, right? So where should I place the lone pairs? On the axial or on the equatorial? Where would you like to place the lone pairs, children? They need more space. They can cause more repulsion. They should be more away from rest. Axial is this, these two axials. This one. These two which are standing perpendicular to the base. They are axial. Everybody is saying place them on the axial. That is wrong. That is totally wrong because axial is making 90 degree angle with the base. So you should not place it on the axial because axial is going to make 690 degree angles. It's better to place them on the equatorials because they are making 120 degree angle. Because equatorial has a bigger angle. They are more away from each other. So children, those who are saying axial, try to understand this. Axials, they are 90 degree and there are 6 such angles, 90 degree. So when you put lone pairs on the axial, then they are going to repel from 5 other atoms by an angle of 90 degree, right? Lone pairs will repel with the other atoms by an angle of 90 degree. But if you put them on the equatorial, then equatorials are going to repel with other 3 equatorials by an angle of 120 degree, which is bigger, less repulsion. So let's write down lone pairs should always be on the equatorials, right? Okay, now let's try to understand this. So all 5 atoms, no lone pair. Then the structure will be a perfect trigonal bipyramidal. No distortion like this. All 5 atoms. So it is trigonal bipyramidal. You can write TBP. What can be the next? Tell me what can be the next? 4 atoms and 1 lone pair. 1 lone pair. Where would you like to place the lone pair, Aslisha? Let's place it here, over here. Remove this bond. Then what is left? Can you see this, children? This one. Is this trigonal bipyramidal? No. These are molecular geometries. Is this trigonal bipyramidal? No. What is it? It has a very popular name. You know this thing in the parks? A child sitting here, a child sitting here. What is it called as, children? Seesaw. 4 atoms with 1 lone pair. See, scientists, they were also human beings, family members. They used to have children, and they pick up all these things from the nature also. So they named this structure as seesaw. Otherwise, the scientific name should be distorted tetrahedral. It's tetrahedral, 1, 2, 3, 4 lone pair. So they call it as distorted tetrahedral also. But the popular one is this. I'll take 1 extra minute, children, to finish this topic. So please stay in the class. Then these are 4 atoms and 1 lone pair. Now 3 atoms and 2 lone pairs. So where would you like to place your 2 lone pairs? Let's place them here. Here, equatorials. That's where we can place. So I'm placing them symmetrical here. So what is left? Can you see what is left? It's an alphabet of English. T-shaped. T-shaped. Like this, right? Which you can see like this. It is T-shaped. The molecular geometry is T-shaped. And then the last 2 atoms and 3 lone pairs. Who is going to tell me what is it? All the 3 lone pairs will go on the 3 equatorials. So place the lone pairs here, here, and here. What is left? What is left, children? Linear. This is linear. So in the next class, which will be on your Tuesday, I will be starting with this. I may request you to come review this particular session on your Saturday, Sunday. Review it completely because I will be finishing with VSEPR and then I'll start discussing resonance and hybridization and unit 2 will be done completely. Okay. Please finish your unit 1. This Sunday, I will declare the result. See you then. Bye-bye. Anyone has any questions? Stay back. Aslisha?